Hmm.
Perfect. So that will, soon some more people arrive. So, so, so you just have your usual handwriting on the
Yeah, yeah.
people,
It's not quite as good as a blackboard because it doesn't stay there in the way that a blackboard does, but that's the best
but
I can do on Zoom, I guess.
sometimes people, what they do, they somehow do some program where they take your handwriting and make it a bit like more fancy, right? So,
Ah,
right. So
I
in
don't know. I
addition
don't know
on
about that.
handwriting, on top of it, they run some program which changes it
Oh, I didn't
kind of,
know I could do that.
yeah. So this can be,
Yeah.
but maybe good. We in good shape maybe to start. Welcome everybody. It's a great pleasure to have back Matthew Kwan from ISTA in Vienna, Austria. And he will talk about coloring random Hasse diagrams and box-Delaunay graphs. Please, Matthew.
Thanks a lot, Benny. Thanks for the invitation. It's uh, always a pleasure to speak at the seminar, and thanks everyone for coming. Um, so I want to speak about some joint work with Zhihan Jin and Lyuben Lichev. So Zhihan is a PhD student at ETH. Actually, Benny's PhD student, and Lyuben, until recently, was a postdoc here at ISTA, Austria, and he's just recently moved to the group of Fabio Toninelli in the Technical University of Vienna. But they're both really excellent, and I had a really fun time working with them on this topic. Yeah. So the title is Coloring Random Hasse Diagrams and box-Delaunay Graphs, which perhaps there are some words in there that you're not familiar with. That's fine. I'll be gentle in the introduction, and please interrupt me or put a message in the chat or something if you want me to clarify something. This should be a pretty gentle talk. So I wanted to start sort of as motivation by talking about I think the two simplest and sort of most fundamental ways of associating a graph with a poset. So I've already written them on the screen here. Do I have a laser pointer? No, maybe not. Interesting. Anyway, so I've got two definitions here. The first one is sort of the obvious way you might try and associate a graph with the poset, the comparability graph. It's where the vertices are the elements of the poset, and you just put an edge between u and v whenever u is less than v. So whenever u and v are comparable. The second thing here is a Hasse diagram, which is actually a subgraph of the comparability graph. So the elements of this poset are, the vertices of the graph are also elements of the poset. And now you put not an edge between all the comparability relations, but only sort of the minimal ones. So by transitivity, there's certain relations that if you know that they're comparable, then you know that the whole thing is comparable. And so I just put an edge between a pair u and v. If u and v, if say u is less than v, but there's no w sort of in between u and v, no w such that u is less than w is less than v. Okay, so probably a picture will clarify this. This is with the coordinate-wise partial order on the plane, which just means that a point in the plane is a pair of numbers x and y. So I say x and y is less than x prime y prime if x is less than x prime and y is less than y prime. So with that you can define a poset just by a set of points in the plane. A two-dimensional poset, and so these set of 4 points. I thought I would have had a laser pointer, but something seems to have. Is this a no? Anyway, so this set of 4 points here defines a poset. So these are the comparability relations, and the Hasse diagram is almost all of them except this long edge here between these points. Although it's a comparability relation, it's not a minimal one because this is less than this, but this and this are in between. Okay. So this is what these are some graphs, comparability graphs and Hasse diagrams. What types of interesting things can we say about them? Well, one really important fact about comparability graphs, maybe the most important fact about comparability graphs, is that they are perfect. In fact, so there's this amazing document, or this article by Paul Seymour about how the proof of the strong perfect graph theorem was found, which I think is a really interesting sort of view into structural graph theory. But so apparently comparability graphs played some kind of a role in that. They're sort of a basic example of a perfect graph. Anyway, the fact that they are perfect was first proved by Mirsky, but maybe not in the language of perfection. But he proved that comparability graphs are perfect. And what that means in this context is that the chromatic number chi is equal to the clique number omega. So the chromatic number is the minimum number of colors such that you can color all the vertices such that no pair of adjacent vertices get the same color. The clique number is the number of vertices in the largest clique. So clearly the chromatic number is always bigger than the clique number, or at least as big as the clique number, because all the vertices in a clique need to receive different colors. But the interesting thing about perfect graphs is that the converse is also true. So you can completely determine the chromatic number by local considerations. And these things are important in structural graph theory.
Maybe it's true for them and their induced subgraphs, right? It's important.
Right. But so comparability graphs are hereditary. So if a graph is a comparability graph, then every induced subgraph is also a comparability graph. So it suffices just to check this property for comparability graphs. Yeah, but in general, the notion of being perfect does need something about induced subgraphs. So that's a great theorem. And so you might wonder, maybe Hasse diagrams are also perfect. That would be nice. If you think about that for a moment, you realize that the problem with that kind of a thing is that Hasse diagrams cannot have very interesting clique number. So it is an observation, really just almost by definition, that Hasse diagrams are triangle free. So the largest possible clique they can have has two vertices. And this, perhaps I'll let you convince yourself why this is true. It's basically because posets are transitive. So if you think about three vertices, x, y, and z, what would it mean for them to form a triangle? Well, you'd have to have like x is less than y is less than z, and then, xz is not an edge of the Hasse diagram. Anyway, so if Hasse diagrams were going to be perfect, that would be tantamount to the claim that, is the chromatic number at most 2. So the only way that Hasse diagrams could be perfect would be if they're always bipartite. And that's not true. So here's a picture, again, using the coordinate-wise partial order on the plane. If I consider this set of points, hopefully I draw it correctly, then the edges of the Hasse diagram, you can check are these ones. So all other comparability relations are sort of not minimal. That's a 5 cycle. It's not bipartite. So it is not true that Hasse diagrams are perfect just because they're not bipartite. But you might still ask for, maybe they're not perfect, but maybe they're at least, chi-bounded. Maybe at least the chromatic number is bounded in terms of the clique number, which in this case is 2. So you could ask, and apparently this was first asked by Burmeister and Rival. You could ask, maybe the chromatic number is bounded by some constant. C. Yeah. So this one is a harder question. It's not so easy to think about just by drawing little pictures like I have done. But unfortunately, even this is false. So it was, at this point, well, it's kind of a classical theorem. It was proved in the 70s independently by Bolobash and by Neshetril, I need some of these, and Rödel. That is not true. There are Hasse diagrams which have as large chromatic number as you like. So their proofs were different, but Bolobash's proof happens to be very closely related to Erdős's proof that there are graphs with arbitrarily high girth and chromatic number. So there's this probabilistic proof of that, and there's some clever way to embed these types of graphs in a Hasse diagram, and that's Bolobash's proof. Anyway, so these things are very far from perfect. The chromatic number is not bounded at all. There's still all sorts of questions that you could try to ask to sort of follow up on this. So the next thing that was proved here was by Brightwell and Neshatril, which sort of looks similar but is actually stronger. That there exist n-vertex Hasse diagrams with independence number alpha being little over n. So if you know that the independence number of a graph is much less than n, then that automatically tells you that the chromatic number is large, just because the color classes are always independent sets. But the converse is not true, so this is really a stronger statement. And really this is saying that the fractional chromatic number of Hasse diagrams can also be large, not just the chromatic number. And the other direction that you can ask about is, well, what about quantitative aspects? So we know that the chromatic number of a Hasse diagram can be unbounded, but maybe it still can't be very large as a function of n. So these theorems of Bolobash and Neshatril were not written in a quantitative way. You can get some sort of quantitative stuff out of them, but a better theorem was at some point proved by Janusz Pach and Istvan Tomon, who proved that we can have the chromatic number being at least log n. So the chromatic number can grow at least as fast as log n in an n-vertex graph. And this was proved via the independence number. So this also proves sort of the Brightwell-Neshatril version of things, that the independence number is at most n over log n. But that's still pretty small. Log n is still a pretty small function of n. But I think, very surprising next development here, which I think surprised a lot of people here, is that actually the chromatic number is really far from bounded. Actually, we can have the chromatic number being as large as n to the 1/4. Yeah. So it's not hard to see, and maybe I'll leave it as an exercise to see why the chromatic number is sort of easily always at most square root n. So it's some non-trivial power of n, and so this shows that that power is at least 1/4. So this is currently the state of the art. The answer is between n to the 1/4 and n to the 1/2. And of course, it's still interesting to know what the right exponent is, but we have a pretty good idea that at least the chromatic number can grow polynomially fast. And this is a pretty surprising. So this is not proved by like sort of constructing a poset in some like well, the proof is constructive, but it's sort of by some equivalent definition of some equivalent characterization of what a Hasse diagram is. You construct some graph, you show it happens to be a Hasse diagram, and therefore this is true. Yeah. So this is still an interesting direction, but really the direction that I want to talk about today is
yeah. So their graphs will be geometric, right? So
yes,
from geometry, and that's why they kind of easily saw that it's Hasse diagram of something, right?
Yeah. So there's like some characterization about orderings with the vertices and some configurations that appear, and there exists an ordering with some properties, and so they show that it satisfies those, which sort of doesn't obviously reveal what the poset is, just that it's a Hasse diagram. I mean, you could sort of construct a poset somehow. But so I think Jacob Istvan told me that Jacob also has a different geometric construction that he believes might have polynomial bounds, but doesn't know how to prove it or something like that.
Nice. Okay.
Anyway, so the direction that I really want to talk about today is similar types of questions, but under a bound on the dimension of the poset. So this type of question was apparently first asked by Neshatril and Trotter. Well, exactly these types of questions. What about Hasse diagrams of low-dimensional posets? And just to briefly remind you what the dimension of a poset is, well, so far we've seen two-dimensional posets because they can be embedded in the plane, and the dimension is just the smallest dimension of space you can embed them in. So the dimension of a poset P is the minimum D such that P can be represented as the coordinate-wise partial order for some point set in R to the D. So if you can realize it geometrically in D-dimensional space. Equivalently, this is the same as saying that it can be viewed as sort of an intersection of D linear orders. Yeah. So bounded dimensional posets, so especially two-dimensional posets, you can view them as sets of points in the plane where you sort of put an edge you put an edge between 2 points if there's sort of no points in between them in some appropriate sense. So somehow two-dimensional posets at least look a little bit like planar graphs. So the sets of points in the plane, and you put edges when things are sort of not obstructed in some sense. They're not quite planar graphs, but they feel kind of planar. And so maybe that should be some justification for why you might believe that the chromatic number might be bounded, if not for general posets, but at least for bounded dimensional posets. So maybe two-dimensional posets are something like planar graphs. Yeah, so perhaps on the subject of planar graphs, it is a good moment to mention a different class of graphs that also appeared in the title of this talk, namely Delaunay graphs, which is sort of a class of graphs that came from a quite different origin, but turned out to be very closely related to Hasse diagrams. So these are defined in terms of geometrically in terms of convex bodies in Euclidean space. So the definition of a Delaunay graph is in terms of so let curly C be a family of convex bodies in some Euclidean space, and let P be a finite set of points in the same space. Then the Delaunay graph, parameterized by C of P, is the graph with vertex set P and an edge PQ whenever there exists some convex body in my family with C intersect P, sorry, not that, C intersect P being the set PQ. So I've got some collection of convex bodies, potentially an infinite collection of convex bodies, and I put an edge between 2 points if there's a way for me to encapsulate these 2 points in one of my convex bodies without accidentally capturing any other points. Okay, so the most well-known example of this is if I let curly C be the set of disks in the plane, then, well, so if I have a set of points, actually, if I have a set of points in the plane, then what this is saying is I put an edge between 2 points if I can draw a ball around them like this without accidentally capturing any other points. So these 2 vertices here form an edge. On the other hand, this vertex and this vertex, they do not form an edge because any ball I would put around them accidentally captures these 2 points in the middle. Okay. So that's a Delaunay graph. So in this particular case where the convex body is disks in R squared, it's not hard to see that in this case, Delaunay graphs are always planar. In fact, they're a very special type of planar graph. It's a triangulation of the set of points called the Delaunay triangulation. Has lots of special properties, very important computational geometry. So So at least if you make this choice of curly C, you do get planar graphs, so they have bounded chromatic number. Perhaps the second most important example, which is the one that's really relevant to the talk today, is what if I let C be the set of axis parallel boxes? And in any dimensional space. Right. So meaning it's the collection of all convex bodies obtainable as a product of intervals in each dimension. Okay. Now the crucial fact here that makes them relevant to us is that in this case, the Delaunay graph of P can be interpreted as a disjoint union of 2 to the d minus 1 Hasse diagrams. So somehow Delaunay graphs with respect to boxes, which I'm just going to call box-Delaunay graphs. Sometimes they're also called rectangular visibility graphs for some in the computer graphics literature. But box-Delaunay graphs are sort of basically the same as Hasse diagrams. They're a finite union of Hasse diagrams. So in particular, if you're interested in chromatic number, at least boundedness of chromatic number, it's sort of equivalent to think about Hasse diagrams and Delaunay graphs. So just to make sure this is clear, so I thought maybe let me consider this picture here. So we had here these 5 points. These 5 points in the plane. They gave me a Hasse diagram. So all these red edges, they're also points of the box-Delaunay graph, and you can see like each of these red edges, I can draw a box around them that contains just those 2 points and nothing else. They're not the only edges. There's some other edges, and in this case, it's these 2 edges. So you've got the red Hasse diagram, then you've got the blue graph, but the blue graph is actually also a Hasse diagram. It's just in like when I flip one of the directions of the so if the x-axis goes that way instead of that way, then this will be the Delaunay graph. And so in general, you can do this if you have a d-dimensional Delaunay graph. There's 2 to the d minus 1 ways to flip axes that sort of don't get you just the reverse of what you got before, which would do nothing. And so you get a bunch of Hasse diagrams. Okay, yeah. So maybe this sort of geometric context makes it maybe even more believable that bounded dimensional Hasse diagrams, bounded dimensional box-Delaunay graphs, they're geometric types of things that at least closely related things are planar. So maybe they're planar, maybe they have bounded chromatic number. They do not. So it was proved. Oops. Let me use the pen. Oh no. It was proved by Kriz. He's got that on the I. Kriz and Neshitril. And not a very easy paper, I think, that 2-dimensional Hasse diagrams and therefore box-Delaunay graphs can have arbitrarily large chromatic number. Okay, so 2-dimensional, I mean, that's the strictest assumption you can make on the dimension because 1 dimension is completely trivial. So even under the strongest dimension assumption, you still don't get a bound on the chromatic number. Yeah. So maybe a clue to this should have been that planar graphs, that they don't just have bounded chromatic number, but they're actually degenerate. So like the average degree of any planar graph is bounded. It's easy to see that's just not true for Hasse diagrams. You can get very large complete bipartite graphs. Well, a Hasse diagram can be a complete bipartite graph. So although complete bipartite graphs do have bounded chromatic number, somehow there's something quite different going on than there is for planar graphs. Anyway, so that's the chromatic number is not bounded, but you can still ask more questions, just like we saw in the unbounded dimensional case. For example, it was asked by Matuszek, and I don't know how to pronounce this name. Matuszek and Privativi, can we have the independence number being a little open? So the Krzyzewski construction is not like that. It does have the independence number is linear. You can ask whether you can do this. So this question was answered in a really nice paper by Chen, Pach, Szegedy, and Tardos, which really proved a lot more. They didn't just prove that it's possible for a bounded dimensional Hasse diagram or for a two-dimensional Hasse diagram to have sublinear independence number. In fact, they proved that it almost always happens. So they sort of initiated the study of random Hasse diagrams, or at least random two-dimensional Hasse diagrams, which is a certain type of geometric random graph. So for a random two-dimensional Hasse diagram or a box-Delaunay graph. So as you might imagine, that just means so it's generated by n uniformly random points in the unit square. Yeah, so I just independently take n samples of a uniformly random point of the unit square. Then with high probability,
should the exponent be 2 rather than n?
Yes,
1.
it should definitely be 2 rather than n. Oops. There's this like a pencil, which is slightly harder to read than the pen, and I keep accidentally choosing it. Anyway, so with probability tending to 1 as n tends to infinity, they basically know what the independence number and actually the chromatic number are up to lower order terms. So at least to answer this question of Matuszek and Privativi, they proved that the independence number is always big O of roughly n over log n up to some log factors, log squared. And they had an almost matching lower bound. So this is almost the best you can get with random Hasse diagrams. Sorry, not a big O, it's a big omega. So they had also n over log n, but now even more complicated, log n, log n. Okay, and they managed to prove a similar thing for the chromatic number. So I'm just gonna write, so it's basically log n over log, well, it's whatever you would expect given whatever above, log n, and log n over log n squared. Okay.
Just to be sure, right? You just drop n points uniformly at random, and then you look what Hasse diagram it gives based on this usual.
Exactly. Yeah, or the Delaunay graph. So they really studied the Delaunay graph, but their proofs work basically the same way for Hasse diagrams. There's a small wrinkle actually, a difference between Delaunay graphs and Hasse diagrams, which I'll get to in a second. But yeah, that's the model. Yeah. So this obviously this answers this Matuszek Privativi question, and as far as we know, this is the best sort of bound you can get. So we don't know any better bounds than what you can get from random Hasse diagrams in bounded dimensions. I have no idea whether you should conjecture that's the best or not. But sort of in addition to the fact that
is it a good reason to believe that it would be logarithmic? Because I think people believed it before, so maybe on usual Hasse diagrams, and it's jumped to power. So what you feeling?
Yeah, so I think different conjectures have been made. I think there exist conjectures in both directions. I think like personally, I think a lot in terms of random objects, so it seems natural to me that this might be best possible. But the fact that there's this weird geometric construction that gives n to the 1/4, maybe there's weird geometric constructions in bounded dimension. I don't know. It's hard for me to think about. I always find it really hard to make predictions about the space of all possible graphs because it's just there's so many crazy things that you can do. So I will maybe punt on whether I believe this is optimal or not. Anyway, it is a bound. But I think apart from the fact that it's an answer to the extremal question, this is a really interesting model of random graphs, and the proof of Chen-Pak, Szegedy, and Tadós is really interesting. So it's a little bit like random geometric graphs. So for a random geometric graph, you take a random set of points and you put edges between points that are sufficiently close. This is sort of has that flavor, but it's sort of a really unusual geometry because, even if points are very far away, if they're very close in one of the dimensions, then you could have like a very long, skinny rectangle that contains both of them. And so it's kind of like a little bit geometric, but there's some interesting things. So I think this is sort of independently quite interesting from a random graphs point of view. Anyway, so given this work on random two-dimensional Hasse diagrams, I guess the next question is, what about random d-dimensional Hasse diagrams if d is bigger than 2? Unfortunately, this proof does not obviously generalize to higher dimensions. Despite that, they sort of use some special facts about 2 dimensions that are not true in higher dimensions. And I'll hopefully have time to say a few words about what exactly goes wrong. But nonetheless, István Tomon managed to prove, not using random Hasse diagrams, but using sort of a different type of probabilistic construction, but still sort of the same sort of heuristics, that for any d, but let's say I want to think of d as a constant while n goes to infinity. So if a constant d, there exist d-dimensional box-Delaunay graphs. There exist, meaning there is some interesting probability distribution which satisfies this, with independence number at most n over log n to the power of d minus 1 over 2 plus little of 1. Yeah. So as the dimension requirement gets bigger, so as the dimension requirement gets weaker, you can find sort of worse and worse counterexamples to the sort of conjectural behavior. You can make the independence number be smaller and smaller by sort of an increasing power of log. Yeah, and this is not very easy to prove. And another thing is that most of the time there doesn't seem to be that big of a difference between Delaunay graphs and Hasse diagrams, because well, we've seen that a Delaunay graph is really just a finite union of Hasse diagrams. But for this particular theorem, his proof really depended on Delaunay graphs. He wasn't able to handle Hasse diagrams, but he made a conjecture that you can do the same for Hasse diagrams. So he conjectured that, again, for constant d, there exist d-dimensional Hasse diagrams with the same kind of bound, with alpha at most n over log n to some linear function of d for some constant d. Sorry, not d, for some constant c. Yeah, so that you get the same qualitative type of behavior. So our main result, finally, so this is again with Zhihan Jin, myself, and Lyuben Lichev. So we managed to answer this conjecture of Tomon, and in fact, we did manage to actually study random Hasse diagrams, and not just the existence question, but we basically know what is the independence number and chromatic number of a random Hasse diagram in all dimensions. So for a random d-dimensional Hasse diagram or box-Delaunay graph, with high probability, I know that the chromatic number is log n to the power of d minus 1 plus little of 1. And the independence number is, well, the obvious thing you would expect it to be n over log n to the power of d minus 1 plus little of 1. Okay. So this is a stronger result than István's result in several directions. So the bound is stronger. So instead of d minus 1 over 2, it's d minus 1. And it works for Hasse diagrams. And it also works for the uniform distribution for completely random Hasse diagrams and Delaunay graphs. Yeah. So I'm hiding here some log-log factors for basically the same reason as so the Chen-Pak-Szegedy-Tardos proof had all these complicated log-log factors. We have similar log-log factors, except that in the case that they considered, so if d equals 2, we are able to do some sort of use the special structure of the two-dimensional case to improve their analysis and actually get things up to a constant. So the real answer is that the chromatic number is up to a constant log n over log n. So there really is a log n, but only one of them. And the independence number is what you would expect, is n log n over log n. Yeah. So this improves the bounds of Chen-Pak-Szegedy and Tardos in both directions. So both the upper bound and the lower bound were not quite this simple. Okay, so that is our main result. Does anyone have any questions before I start to tell you about the proofs?
So here to consider the random Hasse diagram where you draw random points. Can you say anything about, a sample out of all graphs that are Hasse diagrams, a sample random one? Can you say anything about this?
That's a good question that I don't know the answer to. Yeah, I mean, you could ask this both for uniformly. I think so. I know that a random poset is trivial. Like random posets don't have interesting structure. They're always height 2 or something. So I think a random poset is not interesting to ask about, but a random Hasse diagram might be. I'm not sure. That's an unusual kind of a distribution. I haven't thought about it. Maybe it's interesting. Yeah, good question.
Okay, thanks. Yeah.
So incidentally, you might hope that so for the question I started with, where you don't put a bound on the dimension, you could hope that if you do this random Hasse diagram thing in d-dimensional space, but you sort of carefully choose d to be the right function of n, maybe that might give you good constructions for the extremal question with no bound on the dimension. We sort of hope this. So apparently, so Istvan explained to us that this isn't possible. So this sort of thing is not going to. So you somehow want interesting distributions on poset, interesting distributions on Hasse diagrams, and we don't really have good candidates for those, except in the bounded dimensional case like this. So if you just let the dimension go to infinity, you sort of start to get less and less interesting stuff as the dimension goes to infinity.
But because there are some hidden constants here, because the formula
there's definitely some hidden constants in here,
which grows probably exponentially in D or something.
Probably, yes. Yeah. Very good. So I'll say just a little bit about the proofs. So the proofs are, I mean, there's really many different parts of this theorem. There's really upper bounds and there's lower bounds. The upper bounds turn out to be completely different to the lower bounds, and there's also things that are done differently in the two-dimensional case and the d-dimensional case. There's a lot of proofs to talk about. Let me just try and give you some of the ideas for all of them. So there's sort of the main directions are, so first there's an upper bound on chi, an upper bound on the chromatic number, which implies a lower bound on the independence number. And so this is hardest in the Delaunay graphs case. If you can do this in the Delaunay graphs case, it would imply the Hasse diagram case. And then on the other hand, you also need to prove an upper bound on the independence number, which implies a lower bound on the chromatic number. And that's easiest to do in the Hasse diagrams. That's hardest to do in the Hasse diagrams case. It would imply the Delaunay graphs case. There's a sort of slightly complicated mess of implications here. But let's first talk about the upper bound on the chromatic number, which is maybe the less interesting part, but sort of you can see where these powers of log n are coming from, at least a little bit. So the most important observation is that in a d-dimensional Hasse diagram or a box-Delaunay graph with high probability, the maximum degree is up to constant factors, log n to the d minus 1. So this sort of already tells you why you should expect it. Like the chromatic number is at most the maximum degree, and so this is not so easy to prove, but something that's much easier to prove this for the average degree. So if you're interested in the average degree, this is really just a calculation, because then I just need to know for a random pair of vertices, what's the likelihood they form an edge. And so a random pair of vertices is just two uniformly random points in the plane, and I need there to not be any of my other random points in there. So it's some integral. So some integral over the places these 2 points could be, and it's like the volume under some hyperboloid or something. So you can just check that it's log n to the d minus 1. For the maximum degree, it's harder. And so just to give you a very quick sketch of the proof ideas, because I hope to get to some more stuff as well. The proof is a little bit dynamical. So I want to define an exploration process that gradually reveals the neighbors of a vertex. So I fix some vertex, and I'd like to know what its degree is. So I'd like to show that its degree is not too large with high enough probability for a union bound. So I like fix the position of that vertex, and then I start sort of scanning from left to right, or scanning along one of the dimensions to sort of see where the neighbors could possibly be. And each time I sort of find a point among my set of random points in the plane, that sort of restricts the region that the rest of the neighbors can be in, right? Because if you've got a point in the way, you don't put more edges sort of beyond that point. So each time you detect a neighbor, it sort of restricts the region that you need to look for neighbors in the future. And so it's some sort of random process. And it turns out that you can couple this with a sum of exponential distributions. So there's some sort of Poisson process stuff going on, and then you can use some concentration inequality for exponential distributions, for sums of exponential distributions, to get concentration of or at least to show that the degree of a vertex is not bigger than log n to the d minus 1 with good enough probability for a union bound. Okay, so that sort of already almost gives you the upper bound on the chromatic number that you're looking for. Remember, there's a log-log factor, and the log-log factor just comes from a theorem of Johansson. So we're just using the fact that Hasse diagrams are triangle-free. So Johansson proved famously that in a triangle-free graph with max degree d, we have that the chromatic number is not just at most d, but at most d over log d. Okay. So Hasse diagrams are triangle-free. It is not true that box-Delaunay graphs are triangle-free. So they do avoid cliques of some size. So conjecturally, there is an extension of Johansson's theorem that would do the job, but that's still a conjecture. So for Delaunay graphs, we need to use an extension of Johansson's theorem due to Alon, Krivelevich, and Benny, that the same holds if there are few triangles in some appropriate sense. So there's some robust version of Johansson's theorem. And so you somehow just need to study triangles in these types of exotic random geometric graphs, which is sort of not that easy, but you can sort of accept crude bounds here, because you don't need exactly how many triangles there are. You just need there's few enough that you get the log-log factor. So this sort of upper bound on chi direction, this is a lot of stuff that's sort of the flavor of what you would do in the theory of random geometric graphs. It's a lot of like thinking of random sets of points as Poisson processes, revealing things in certain ways, thinking about regions of points and where they can lie, taking integrals over things, that sort of stuff. The other direction, so the upper bound on alpha is completely different and is much more combinatorial. This is, I think, the most interesting part of the paper, where the most ideas are, but it's also very difficult to describe in a short period of time, so I'll try my best. So if we want to prove an upper bound on the independence number, we want to prove that the independence number is at most k with high probability for some appropriate k, which is going to be like n over log n to the d minus 1. And we're going to do it as usual in random graphs via a union bound over sets of size k. So there's n choose k possible ways to choose k vertices. We want to choose that each individual set. We want to show that each individual set of k vertices is so unlikely to be an independent set that probably the independence number is at least k. So in other words, I want to think of it that k of our marked points, or k of our n points are marked, and we want to show it's unlikely there's no edge between marked points. So if the marked points are like the things that I'd like to show are not an independent set, so I want to show there's likely going to be an edge between them. Okay. So our starting point, I sort of have to tell you about the approach of Chen, Pach, Szegedy, and Tados. What they did in the two-dimensional case. So what they did was to first reveal the x coordinates of all the points. And then, so this is not exactly what they did, but it's sort of, I think, morally similar to what they did, is then I'm going to gradually reveal the binary digits of the y coordinates one by one. So what I mean by that is first I reveal the first binary digit of all the points, then I reveal the second binary digit of all the points, then I reveal the third, and so on and so forth. So maybe let's draw a picture of, let me leave some space because I want to write more stuff here, but let me draw a picture of what this sort of means. Okay, so first I tell you what the x coordinates of the points are. So maybe the points are like along the x-axis, they look like this. We don't know what the vertical coordinates are, but those are the horizontal coordinates. And I know that some of them are marked. So let's say like this one's marked, I don't know, this one's marked, and this one's marked or something. Okay, and so then one by one, I sort of reveal more information about the vertical coordinate. So what that means, so the first digit, it's like splitting the cube. So sorry, this is the two-dimensional square. I split it in half. And for each point, I'm saying like, are you in the top half or the bottom half? So maybe this point lies in here. Maybe this point lies in here. Maybe this one lies in here. Maybe this one lies in here. This one lies in here, and whatever. And then when you reveal the second digit, it's like I split each of these in half again, and I tell you which side of each line they're in. So maybe this point is in here. And this point is in here. This point's in here, this point's in here, and this point's in here, and whatever. Now, I've chosen this example in such a way that even after revealing just two binary digits, you can already see that there is an edge between the marked points. So namely, you can see that there's this red vertex lies somewhere in here, this red vertex lies somewhere in here, and all the black points between them, So the only points that could possibly obstruct between these two marked points is this one and this one. And we've already revealed enough information to know that they sort of got out of the way. So this is here and this is here. So although we don't know the precise position of these two red points, we know there's an edge there. So this can be viewed as sort of a process of like gradually revealing more and more about the vertical coordinates. And at some point, you'll first see, well, and sort of seeing how the edges emerge as you do this. Okay. So why is this good? How can we do this? So each time we reveal a new digit, there are many independent consecutive pairs of vertices that have a chance of becoming an edge. Okay, so it's like I'm each time I reveal a new binary digit, it's like the next round of what I reveal. It's like it's very easy to describe the conditional distribution. It's just so each point is in some, in this particular example, like so let's say these are the marked points I'm interested in. And so the consecutive pairs would be this one with this and this one with this. And so maybe, I don't know, maybe let me extend this example. If I have more red points, then you'd have, more consecutive pairs. And at each step, the consecutive pairs have some chance of forming an edge. So here, sort of this consecutive pair, I wish I had a laser pointer. It's so this vertex and this vertex, if it had happened that these two vertices in between had got a different binary digit as these two red points, that would have made these two red points form an edge. So there's a chance that for two consecutive red vertices, there's a chance they form an edge in the next step. And this is true independently for each consecutive pair. Now, maybe you don't succeed, maybe they don't form a consecutive pair, but then at the next stage, you can reevaluate what your consecutive pairs are and do the same thing again. So in this picture, once we've revealed the second digit, we saw that this vertex and this vertex and this vertex was still a consecutive pair because they still had a chance of forming an edge. They had the same second binary digit. So it had the same first binary digit. But now this consecutive pair is no longer a consecutive pair because we already know that that this vertex and this vertex have a different first binary digit. So we're not considering them anymore. So really, we've sort of broken up our picture into two sub-pictures, the top half and the bottom half, and we independently look at the consecutive parts on the top and the bottom. And sort of this gives us really a way to analyze how edges emerge as we do this process. And the consecutive pairs are the most likely pairs to form edges. So this is capturing sort of a constant proportion of all the probability mass that can form edges we're finding this way. So that's one needs to do calculations and stuff.
Can I ask you,
Yeah.
it's a bit surprising because consecutive pairs are only linear volume from quadratic, and you're already saying
Yes.
that's enough.
Yes. So the key thing is that, so number one, points that are far away are much less likely to be an edge anyway. So by considering the close pairs, like the linear ones, you're actually getting most of things. But also, even far away points, like as this process continues, they'll get closer and closer. So the consecutive pairs at each, like the consecutive pairs late in the process, they could have arisen from pairs that were not consecutive early in the process. Because the things that were in between them ended up getting different binary digits.
Thanks.
Does that at least so
No,
so
that
any
shows that
one
actually you're
calculation.
looking on more edges, right? Not just linearly many, right? You actually eventually look on
Yes,
more.
yes.
Because...
So the key here is that there's like a log factor missing. So in the two-dimensional case, a random Delaunay graph has about n log n edges, and here in each stage you're looking about n of them. But I get to do log n phases of this. Like I get to keep splitting things up into more binary digits until I've completely separated everything, and that takes about log n steps. So I'm sort of recovering that log n. Okay. So now I have basically no time to tell you what our actual new ideas are. So there's new ideas in two directions. One of them is that in the two-dimensional case, we managed to improve that analysis. And the way we did that was so when you need to, at each stage, you need to understand how the marked points, how the red points are distributed within the black points, because that'll change what the probabilities are. So you can make a worst case assumption, which is what the previous authors did, or you can actually try and understand what are the fluctuations of the distances between the red vertices. So the worst case is when the red vertices are sort of equally spaced, but there's going to be, due to randomness, some fluctuations of these distances, and you can benefit from that. And that's how you recover the log-log factor in the two-dimensional case. In the higher dimensional case, really, let me maybe just say what the problem is without saying what the solution is. So in higher dimensions, what is a consecutive pair? So this is really the reason why this doesn't generalize to higher dimensions. So when we looked at consecutive pairs of vertices, we had complete independence between each pair. And there's just no way to do, well, there's no obvious way to do this in higher dimensions. So there's no like linear ordering so that you can like partition them into little blocks and do each one independently. So sort of in a sort of slightly cryptic phrase, what we did to get around this is to sort of do the randomness in a different way. So instead of using the randomness of all the points, we condition on the positions of the unmarked points, the black points, and just use the randomness of the red points. So this gives you much less randomness to work with, but it makes independence much easier to get, because if you sort of freeze the black vertices and just look at the red vertices, then two pairs of vertices are dependent if and only if they share an endpoint. So, you know, you can do some tricks like looking for a large matching and you know, if you can find disjoint pairs, then you have independence. And so there's some inductive scheme that uses that somehow. And
maybe just to understand, so you basically put roughly random endpoints in the square or in the box, and then you add this k, your points, which you make red, and see how they.
Yeah. So you get weaker bounds this way. Like in particular, the log factors are worse because you just have less randomness to show that, like things are less well distributed because you don't get to use the randomness of the black points, but you gain a lot more in the independence than you lose in the sort of amount of mixing that you have. Yeah. So that's perhaps all I will say. And maybe could take some questions.
Okay, so thank you very much, Matthew. Really interesting talk and topic. So yeah, I was asking a lot of questions. So everyone else, you guys can unmute yourself and ask more questions if you. So maybe then I maybe ask some more. So this kind of points in a box with a little bit of structure of product dimension. It's one interesting Hasse diagram in posets. Are there other random, you know, because it comes from the geometry of the object you're working with, right? You can try to look on some other spaces and kind of maybe which are not have product structure and then see what's there. So what else people, just for our education, what else people study?
Yeah, so I'm not really sure. So there's a lot of different models of random posets. So I think Brightwell has a survey on many different models of random posets. It's easy to accidentally design a model which just turns out to be mostly trivial. Like it's easy to accidentally design a random distribution such that almost with high probability you have height 1 or something like that. So I don't actually know other examples of genuinely interesting types of random posets. Yeah, but I'm not like the necessarily the expert in this area, so that doesn't mean there aren't any.
So then here is the only question which is left is in higher dimension, maybe really nail the distribution or right, results in terms of logs and things like that, right? Otherwise you.
Yeah, so it seems to us that the way that we got ourselves independence in higher dimensions, like the way that we counted this dependence issue, sort of fundamentally is losing logs. So yeah, maybe it's doable. I don't know, but we didn't see how.
Actually, since you mentioned, so imagine I forget for a second about random posets, right? So we go back to this, say, two-dimensional Hasse diagrams of two-dimensional posets. So for trivial Hasse diagram for chromatic number, because it's triangle-free, there is a trivial bound of square root n up to logs. So if I tell you that the dimension is 2, yeah, I don't know if it's power or log, but is it known to improve the square root n?
Yes. There is a very ingenious proof, actually from the sort of computational geometry literature, where this question actually originated. So the question sort of originated from two different directions, from like the extremal combinatorics, Bolobash type of stuff. And And also from computational geometry, they care about this because of its relation to something called conflict-free colorings, which is some computational geometry thing. Anyway, so they found some very interesting recursive way to so as you said, by you get trivially a bound of square root n, you can think of this as being like Erdős-Székely or something. They found some very tricky way to sort of partition the grid and apply Erdős-Székely like inside each grid cell, and then somehow combine things and then recurse on this. So the best bound is some power of n that is not 1/2. So it's some beta power of n, but still very far from log n.
Okay.
Yeah, and I really don't know what to believe is the answer.
Okay.
Yeah, it sort of feels like like Hasse diagrams feel like they are mostly bounded dimensional objects, except for the fact that you can get large complete bipartite graphs. So the reason you can get that is like if you take a bunch of points like this and a bunch of points like this, then you get every pair of edges between here and here is gonna be an edge. But it somehow feels like this is kind of the only way to get something that's not sparse. So it feels like there should be some way to play with this, but I don't know it. Yeah.
Okay. Interesting.
Yeah.
Sorry, maybe a naive question. So how large is the difference between the chromatic number of Hasse diagram and the say planar graph or planar graph in higher dimensions, like three-dimensional graph?
Good question. Actually,
Because the chromatic number of planar map can be calculated exactly. Well, I'm not sure whether some people calculate the chromatic number of the high dimensional graphs.
Yeah. I am now realizing that I also don't know.
But what is the definition of high dimensional graph? Because I think in 3 dimension you can embed any graph, right? So
Right, but for random, I guess.
I'm not sure because you can define the high dimensional of posets, the dimension of posets. I think you can define you can like generate the idea of planar graph to high dimensions. I'm not sure whether it is true or not.
Yeah, so for example, you could ask about, instead of the Delaunay graph with respect to boxes, you could ask about the Delaunay graph with respect to balls. And that's guaranteed to be planar. And then in higher dimensions, you could ask, what's the chromatic number of a random one of them? I would imagine someone's worked that out. I don't know it.
Okay. I just know some two-dimensional cases and wonder well that problem can also be generated to high dimension or not.
Yeah. Any question?
more questions? If not, let's thanks Matthew again. Thank you again, Matthew. I think we can stop recording.